Hello, and welcome to Module 11.2c, Transformations of Quadratic Functions, Multiple Transformations. Our objective today is that I can apply multiple transformations to quadratic functions, and I can use transformations to identify quadratic functions from graphs and write equations of quadratic functions. All right, so the first thing that we're going to be looking at is vertex form. And what is vertex form? It is this specific format here of a quadratic function. F of x is equal to a times the quantity x minus h squared plus k. So this is combining all of the transformations that we have done into one equation. And it's an incredibly powerful version of a quadratic equation. The standard form works great, does a lot of things. Vertex form gives us a lot of very specific information. So the first thing, it's going to tell us how much it is stretched or compressed and whether it's reflected or not. So if it's stretched or compressed, we're looking at that a value to see where we are stretching or compressing and if we are reflecting across the y-axis. So that all comes from that piece right there. The value of k is going to shift or translate the parent graph up or down. So this value is involved with our vertex. So if it's positive, we move the graph up. If it's negative, we move the graph down. H is going to translate the graph left or right. So if we have a plus sign in between there, we are moving it left because it's that double negative. We're subtracting a negative. And if it's just x minus h, we are moving it to the right because h is a positive value. So I want to highlight the fact that these two pieces together, these change the vertex. Okay, those two pieces, k and h, those are what is going to change the vertex. Whether you stretch it across the x-axis or reflect it across the x-axis or stretch it or compress it, doesn't affect where the actual vertex of the graph is. H and k are the two pieces that are going to change where the vertex of the graph is. And that is why this is called vertex form. The value of writing a quadratic in this form is so that I can look at this equation and I can find my h value, I can find my k value, and I am going to know my vertex. H value gives me the x, k value gives me the y coordinate. Okay? So your vertex comes directly from your values of h and k in your equation. And then you can use that to get your starting point on the graph, to finding corresponding points that are appropriate to use, and all of that. So let's get started. We have f of x is x squared, and g of x is equal to negative 2 times the quantity x plus 1 squared plus 2. So let's first identify what are the pieces that are happening here, right? So my vertex is affected by this and this. So I am going to, remember, that's a minus a negative 1. So I'm going to shift left 1 and up 2, right? So we're going to move to the left 1 and we're going to go up 2 for our vertex, right? So we're going to put that in the center box here. Okay, so we're going to start with left 1, so we'll be at negative 1, up 2 will be at a positive 2. That's my starting point. Okay, so now we need to figure out what else are we going to do here, right? And let's actually also pause and go back and see why is this our starting point. So if I substitute in negative 1 for my x value, right? Negative 1 plus 1 is going to be 0. 0 squared is 0 times negative 2 is 0. So now we have that original point and we're going to shift it up 2. 0 plus 2 is positive 2, which is why a negative 1 gives me a 2 for my y value. And I put it in the wrong box because that's going to be over here, right? So our original is this is our y, this is our y prime in these notes. All right. In the assignments, you'll see it labeled as f of x and g of x. So you have a little bit of a distinction. All right. Now that we have that, let's fill in what our other values are going to be that we're going to use. So we have 0 and 1 on the right side of the graph, and -2 and -3 on the left side of the graph. And now that we have all of these values, let's figure out what would the values of our y value be in each of these cases in the original graph. So y to the 0 power, or 0 squared is 0. 1 squared is 1. -1 squared is 1. -2 squared is 4. And -3 squared is 9. So we see the vertex used to be here, right? This used to be my vertex, but now it's -1, 2. We've gone to the left 1 and up 2 from the origin. So now we need to find what are our values for the new function. So we still have these same values that we can work with. We're going to the left 1 and up 2, but then we need to reflect them and dilate them. So if we substitute in 0, 0 plus 1 is 1, squared is 1, times -2 is -2, plus 2 is 0. So I still have a point at 0, 0. It's just no longer going to be our vertex. 1 plus 1 is 2. 2 squared is 4, times -2 is -8, plus 2 is -6. Now, since I set my graph up so that I'm in the middle here, so we'll do -2 plus 1, I already know that's going to be 0, but we're going to work our way through the math anyways. -2 plus 1 is -1, which you square and you get 1, times -2 is -2, plus 2 is 0. And so we don't have to work our way through -3 because it'll be the equivalent of having a 2 there inside the parentheses total. So those are our new points. So let's graph our original graph, which is your typical x squared graph. We have a point at 0, 0, 1, 1, 2, 4, and 3, 9. -1, 1, -2, 4, -3, 9. That's my original graph. All right, that's our original x squared graph. Now let's graph our new points. We have a point at -1 and 2. So that's right there. We have a point at 0, 0. We have a point at 1 and -6. We have a point at -2 and 0. We have a point at -3 and -6. So I'm going to go ahead and draw my curve in. And we extend our line to the edge of the grid. And we are going to make sure there's arrows on the ends of it. All right, so let's pick a point and let's trace the pattern that we're taking with it. So we're going to start order of operations. We need to start inside the parentheses. So I'm going to start with this point right here. Right, we're going to actually see if I can, I probably won't be able to grab it. We're going to start with this point here, and I'm going to use my laser pointer to show the changes. So we moved to the left 1. So there's my new point. Then, if we're doing order of operations, we did what's inside parentheses first. Now we do what's outside the parentheses and multiplying by it. So we multiply this by -2, and we go down to -8. And then we shift it up 2, and we get to our new point right there. Okay, so my left point, we move it to the next point, we move it to the left 1. We multiply it by -2, and then we move it up 2. And now that one becomes our point at our new, or at the origin, but it's no longer the vertex. Well, what about that original vertex? We move it to the left 1. We multiply it by -2, and then we move, which is 0 times -2, and then we move it up 2. So that's just a tracing of where these points are going, right? Do I expect you to actually physically trace out that this then doubles and then moves up? No, most likely I'm not going to have you guys walking through the steps that way. You're not going to have to do it. At this point, we're going to be substituting into our equation and using our calculators and using our arithmetic to find where these points are going to be. All right, so let's look at letter B. I want to find out what's happening here. So the first piece is this. And again, this is minus -1. So we're going to be going to the left 1. What else are we going to do? We're going to stretch by 2. So we're going to double everything. So let's find our points. Our new vertex, if we're just moving it to the left of the origin, right? And let's start off. Where's our original graph? We have our vertex at the origin, 1, 1, 2, 4, 3, 9, -3, 9, -2, -2, 4, and -1, 1. So if we are looking for my origin, if I'm just moving that spot to the left 1, I'm now at -1 and 0 in my new graph. So then I'm going to put in my points, 0 and 1, -2, -3. If I'm looking at my original graph with those corresponding values, 0 squared is 0, 1 squared is 1, -1 squared is 1, -2 squared is 4, -3 squared is 9. And those are the points that I can see graphed right here, right? That is these points, these 5 points right there are what is represented by those red y values. So now we need to find what are the rest of my new y values, the ones that apply for g of x, where we are shifting to the left 1 and we are doubling. So 0 plus 1 is 1, and 1 times 2 is 2. 1 plus 1 is 2, squared is 4, times 2 is 8. And I know, based on my properties, right, we had our origin in our new graph is right there. Not right there. I put a square around. That was the original vertex. This is the new vertex, right, at -1 and 0. So that is going to be the place that we are going to be changing around. So we have -1 and 0. We have 0 and 2, and we have 1 and 8. To the left, we have -2 and 2, and we have -3 and 8. And so we can see our graph right there, right? And we can see that it just shifted it to the left from the original graph, and we stretched it a little bit, so it's a little bit narrower, you can see, but we also just moved it to the left. All right, we're going to go to the next page now, and there are 2 U-try problems that I would like you to do on your own. And then you're going to check your work against mine once you are done. So letter C, let's start with finding what is happening. What is my new vertex going to be? So I have a -2 and a -3. So we're going right 2, and we're going down 3. My original graph is here, 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 and here. That, and that. All right, there's my original graph. So if my vertex is moving to the left, or sorry, to the right 2, my x value is now +2. And if I'm going down 3, my new y value is -3. So we have +2, -3. Okay, what else is happening to this graph? Because we do have a negative sign out here, and so that's going to be reflecting. So we are going to reflect it across the x-axis. All right, so let's do some filling in. So we've got 3 and 4, and we've got 1 and 0 as our points that we're going to work with on our new graph. And so if we put in those corresponding points from the original, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So if we go back to our calculation, 0 minus 2 is negative 2, squared is 4. But then we take the opposite, and it's negative 4. Minus 3 is negative 7. 1 minus 2 is negative 1, squared is 1, and then we take the opposite of it, so it's minus 1 minus 3, and that's negative 4. Value of 3. 3 minus 2 is 1. 1 squared is 1. Take the opposite, it's negative 1. Minus 3 is negative 4. 4 minus 2 is 2. 2 squared is 4. Take the opposite, it's negative 4. Minus 3, negative 7. So I can graph these 4 additional points. We have a point at 0, negative 7. We have a point at 1, negative 4. We've got the 2, negative 3 already. 3, negative 4. And 4, negative 7. And we go ahead and we graph our lines. So we'll do the kind of laser trace on this one. What's happening, my origin is moving, or well, let's look at our point right here. Okay, so, or no, we'll do the vertex. Start with the vertex. We are moving it to the right 2, so we go 1, 2, so that's its new spot. Then we take the opposite of it. Well, the opposite of 0 is still 0, and then we do go down 1, 2, 3 to our new point. Okay, this one we go to the right 1, 2. We multiply it by negative, so we go to negative 1. And then we go down 1, 2, 3. And that's where we get that point there, right? So you can trace these along, you can follow the steps, but in the end, what you're going to want to do is you're going to focus on these 2 pieces here to find your vertex, and then you look for points on either side, and you just simply calculate it. All right, letter D, I'm going to graph the first one real quick. We have 0, 0, 1, 1, 2, 4, and 3, 9. All right. So we've got our original graph there. What's happening? We have a minus 1 and a minus 3. So we're going right 1, and we're going down 3 again. So we're going right 1, we're going down 3, but what else is happening? We are going to compress by 1/2. All right, so right 1 means now we're at positive 1. Down 3 means y value is negative 3. That's my new vertex. Okay, so we're going to put that point in at positive 1, negative 3. There's my new vertex. So let's pick some values around it. So let's do 2 and let's do 3 for now, because I want you to see what's going to happen when we work with this equation. So first of all, let's fill in what we already know. 1 squared is 1, 2 squared is 4, 3 squared is 9. Those are our 3 points to the right of the origin on our existing setup. Okay. So now let's figure out what are those points on our new graph. So 2 minus 1 is 1. 1 squared is 1. Times 1/2 is 0.5. And then 0.5 minus 3 is negative 2.5. But you might be saying to yourself, hey, Mr. Boland, we multiplied by a fraction of 2, but then we used an even number. We should have been able to do that, and it would have given us a nice round figure. This seems weird. Well, let's look at the next one. 3 minus 1 is 2. 2 squared is 4. Times 1/2 is 2. minus 3 is negative 1. What's the difference here? Why did an odd number on this problem give me an even outcome, or like a non-decimal outcome when we multiplied by 1/2? And the reason for that is because of that minus 1 here, right? So if we're using some number sense and we're thinking about using values that can give us clean arithmetic, right? If I see that I'm subtracting 1 from my x value and I'm multiplying, or I'm multiplying by 1/2, so I'm dividing by 2, I would want to get an even number in the end. And I know there's no odd numbers that are going to multiply together to give me an even number. So I need to come up with evens. So what would I do? I substitute odds in for x, because then I'm going to get an even number that I'm going to square and I'm going to be able to divide by 2. So on the other side, right, instead of going immediately to 0, right, because 0 minus 1 gives me negative 1, let's go to negative 1 and negative 3 as our values. So negative 1 squared, if we go for our original graph, negative 1 squared is going to give us 1, and negative 3 squared is going to give us 9. And basically what we did was we skipped over the origin in finding these points, because we really don't need the origin of the original graph. It doesn't really matter for us anymore now that we found where our new origin is. So negative 1 plus 1 is 0. 0 squared is 0, times 1/2 is 0, minus 3 is negative 3. That's not right, because that's our that's our vertex. All right, negative 1 minus 1, that's what I did. I did 1 minus 1. Negative 1 minus 1 is negative 2. Negative 2 squared is 4, divided, or times negative 1/2, or sorry, 4 times 1/2 gives me 2. 2 minus 3 is negative 1. Negative 3 minus 1 gives me negative 4. Negative 4 squared is 16. 16 divided by 2 is 8. 8 minus 3 is 5. All right, so now let's graph some of these points. Okay, so we have negative 1, negative 3 already graphed. We've got 2 and a negative 2.5, so that's like right there. We have a 3 and a negative 1, which is right there. We've got negative 1, negative 1, and negative 3, 5. Okay, well, we got some weird points here to work with. So let's just start. Where is my axis of symmetry? I'm going to just draw it in so that we can work with it a little bit, because I gave you kind of a different combination of points, right? I didn't give you the exact same points on to the left and to the right, but this is where your advantages of using quadratics happen, because we've got this line of symmetry. So this first point that I graphed right here, I can reflect that across my line of symmetry or axis of symmetry, and it's a point right there, right? Our next points are corresponding to one another. We both have a point at negative 1. They're both 2 points away, or 2 units away from the line. So then we go to this next point that's at negative 3, positive 5, and it's 1, 2, 3, 4 points away from our axis of symmetry, right? 1, 2, 3, 4. So then I need to go 1, 2, 3, 4 to my next point that we're going to reflect right there. And so now you can see we draw this in, and we can see the change in these lines. We can see how this is shifted down, it's shifted to the right, and it's now wider because we multiplied by 1/2. It is a wider graph. So try to be thoughtful and mindful of the values that you're substituting in and what they're going to be able to give you when you're dealing with the fractions. And this is where having a strong number sense, having a strong idea and connection to how the numbers are going to be manipulated is certainly going to help you simplify your work in these kinds of problems. All right. So let's look at letter A in example 9, apply transformations of quadratic functions. Although they may appear flat, properly designed football fields arc to allow water to drain. Fields rise from each sideline to the center of the field, known as the crown. A cross-section of a football field that is 160 feet wide and has a 1.5-foot crown can be modeled by g of x is equal to negative 0.000234 times the quantity x minus 80 squared plus 1.5, where g of x is the height of the field and x is the distance from the sideline in feet. Describe how g of x is related to the graph of f of x equals x squared. So let's take each of our pieces of our example or of our function and look at them. So the minus 80 tells me we are going to go right 80 feet. The next piece, the plus 1.5, we've got not down, we're going up 1.5 feet. And then we are, oops, I wanted the highlighter tool. We've got this piece, so we are reflecting, and we are compressing by 0.000234. And this is actually something that's very true. Football fields are crowned. So I know when my sophomore team, when I was playing in high school, when we played our first Friday night game underneath the lights of the stadium on the varsity field before they played, our coaches got us in the huddle and had to tell us that they forgot about telling us that the field was crowned. And because our quarterback kept throwing the ball to the sideline and overthrowing every pass on the sideline, because he had to adjust for the fact that he was a foot and a half higher than the people were on the sideline. May not seem like a lot, but when you start throwing the ball and you start having trajectories and you need speed of the game to go, that 1.5 feet can be a difference between a completed pass and an incomplete pass. So this is something that's very real in football stadiums all around the country. Not everyone, but in a lot of them. All right, let's take a look at letter B, bridges. We've got the lower arch of the Sydney Harbor Bridge can be modeled by the function g of x is equal to negative 0.0018 times the quantity x minus 251.5, the quantity squared, plus 18. Describe the transformations that occur as it relates to the original graph, the parent graph of f of x equals x squared. So let's look at each piece in its individuality again. So we have minus 251.5 there, so we're going to shift right 251.5. We're going to shift up 118 feet, I'm assuming. We're going to just say feet, even though it doesn't specify. I'm not entirely sure. And then we have a reflection on the x-axis, and we have a compression. We're going to compress by 0.0018. All right, and we have here a very nice picture of the Sydney Harbor Bridge with the Sydney Opera House in the foreground, a beautiful reflection of both of them on the water in front of it, and a very picturesque sunset or sunrise image of Sydney and the Sydney Opera House. All right, there is a you try problem for you to do on your own, and then you're going to check your work against mine. All right, so a grand jeté is a type of ballet leap in which a dancer starts on one leg, performs a split in midair, and then it lands on the other leg. It is designed to make a dancer appear as if they are floating through air while their center of gravity follows a path that can be modeled by the quadratic function, where g of x is the vertical distance in feet of the center of gravity from the starting point, and x is the horizontal distance in feet. Describe how g of x is related to the graph of f of x equals x squared. And we have the equation in our table graph off to the right there. So we're going to start with that minus 3. So we're going to go shift right 3. We're going to have a shift down of 1.53. We have a reflection, the x-axis, and we are going to compress by 0.17. All right. And we probably should just include 3 feet and 1.53 feet, since the problem did specify we are talking about feet. So that is using multiple transformations and describing what's happening in multiple transformations within a whole system of, or a whole quadratic equation, whether it be in vertex form as we see here, or we've got the standard form that we've worked with in the past. We will revisit this idea of vertex form in lesson 11.5 when we talk about a process called completing the square. And this is one of the values of that method, is to get vertex form. So we're going to come back and revisit this topic when we get to that point. If you have any questions, please feel free to bring them to class tomorrow. Otherwise, I hope you have a great night.